glad the technical difficulties got sorted out. All right. So first, good job everybody on the midterm. Makes a lot quicker to grade that way. So I appreciate that too. Now, if you have any questions about where points were lost, based on the comment I put in Canvas for each of you, then you can just shoot me an email or something. Straighten everything out. Okay. Now, so what's happening for this week is really a review of certain things that were covered last semester regarding the solution of a nonlinear equation. And the reason for that is, the next topic after that will be from chapter 11, solution of a system of nonlinear equations. So these techniques for a single equation combined with some linear algebra lead to similar methods for a system. And so since it's been a while since, a few months since you've seen all that, I figured just do a quick refresher. And also some MATLAB demos. Alrighty. And so for chapter 10, last semester I taught about 4 methods for solving a linear equation, nonlinear equation, form f of x equals 0. Bisection, fixed point iteration, Newton's method, secant method. We won't bother with bisection because that doesn't really generalize well to a system of equations, but the other methods do. So today I'll focus on fixed point, and then, today's Wednesday, so that's all you're getting this week. Monday, I'll do a quick refresher of Newton's method and secant method. So since you all saw this last semester, this might be boring, but you can just tune me out, as you might be doing anyway, so I won't know the difference. Okay, so we're trying to solve f of x equals 0, and we write the equation in this form, x equals g of x. Then we can use fixed point iteration, also known as successive substitution, to solve it. So a straightforward way to write the equation in that form is g of x is defined to be x plus lambda, some scaling constant lambda times f of x, because if you write g of x like this, then you can guarantee that this equation is satisfied if and only if this equation, the original equation, is. So once you have it written in this form, then there's not much to the algorithm. You choose initial guess at the root of f, and then you just keep substituting into g, and that's your new value. Keep going, and use these values to check whether they're converging or not. Once they converge to within some tolerance, for example, maybe the absolute value of this minus this is less than some tolerance, then the iteration stops, and you have a solution, if it converges. And we'll talk about that too, and it doesn't always happen that way. So I'm going to talk about some examples. These are examples that will be familiar to you from last semester. So deal with some MATLAB. Okay. So suppose the first example is solving f of x equals 0, where f of x is equal to x minus cosine x. So we're solving x equals g of x. G of x is just cosine. Right. So I'll just choose initial guess. X equals 1. So for the fixed point iteration, all you got to do is just set the new x equal to a function g of the old x, but in this case, cosine. Okay, I want to have format long for this. Right. And if we see what happens, we just watch how the numbers behave. They're jumping around a bit, so 0.54, 0.85, 0.65, but we'll give it a chance. They seem to be getting a little closer together, not jumping around quite as much. All right, so 0.73, 0.74. Okay. Now at least it's consistently saying 0.73 something, and I'll just keep going. And we do see convergence. It's taking a while. I've done quite a few iterations here. Right now we're up to first 5 decimal places of green. And then little by little, more being filled in. And if we're patient, then we can get all decimal places of green. And it's just about there, eventually. So this doesn't look so good. Okay. All right, so we finally got all decimal places correct. I don't even want to know how many iterations. It says here in the command history, more than, 88 times. Yeah, that's the actual iteration count. So, okay. Now, and a little bit later on, I'll be able to explain why the convergence was so slow. Second example. So we have the function we want to find a root of x squared minus x plus 3/16. So that's the same as solving x equals x squared plus 3/16. Now, of course, so by solving this equation, we just write it like this equals 0. Then, of course, we can solve that by a quadratic formula. And it has, as a quadratic, it has 2 roots, 1/4 and 3/4. Well, let's see what happens when I try fixed point iteration. Hold on a second. All right. So initial guess 0.2. And then I'll have x equal x squared plus 3/16. And let's see what happens. It's really converging faster than the other one. And it's converging to one of the roots, which is 1/4. And actually, you can let this run all the way to convergence to see how many iterations it takes. Okay. Should tell me if I hover over this. Oh, it's not what it was. Not sure why it's not doing it this time. 45 times. Okay, better. Okay, so in that case it converged. But now, it says it's 0.8. That's closer to the other root, which is 3/4. So I do the same thing. It is definitely not converging. Diverging. Getting a little out of hand. So never mind. Now I'll choose another initial guess, 0.7. The other side of 3/4. And let's see what happens. So it ought to converge to 3/4, you think, but it does not. It's getting smaller and heading towards the other root. And if I keep going, we see this converging to 1/4. Kind of slowly, but it is. All right, so in that case, 2 roots, the fixed point iteration only worked for one of them. And it seemed to suck a lower additional guesses to it, or also or possibly diverge. So we need to find out why that would happen, and like why we'd have success in one case and not in the other. Next, we have function we want to root of is solving x plus natural log of x equals 0. So we can just rearrange it and we get this equation x equals minus natural log of x. So if I consider x equals 1/2 and plug that into my function, and I want to find a root of negative. If I substitute in 0.6 into a function, that is positive. So by the intermediate value theorem, a solution exists in the interval 0.5 to 0.6. Also, the derivative is 1 plus 1 over x. And for a positive x, which is the domain of a function, the derivative is always positive, meaning the function is always increasing. So this root in this interval, 0.5 to 0.6, has to be unique. So this is a one-to-one function. Okay, so let's see if we can find that root. So I'll just choose the midpoint of this interval where we know root exists. All right, so I do x equals minus natural log of x. All right, still in the interval. But now we're outside the interval. That's not good. And it keeps getting worse. Now we have a negative value of x, and natural log is not defined there, so now we get a complex value. So this bombed. Okay. So what we can do is, instead of using this equation, so here I just move to minus to the other side for convenience. Now I take the exponential of both sides. So now we get the equivalent equation, x is equal to e to the minus x. So I can use this as my g of x, because it's still in the same form. The equation is x equals g of x for some g, just a different g. So if I set x back to 0.55, I can do e to the minus x. Now let's see what happens in this case. At least it's staying within the interval, and now it appears to be converging. And indeed it is. Okay. So the thing to keep in mind is, before we're using minus natural log of x, now we change to e to the minus x. Those two functions are inverses of each other. So if x equals g of x fails, then we can try x equals g inverse of x, and that should succeed. All right. One more example. This is my function one root of x minus cosine x minus 2. So I write it in the form g of x equals g of x. This is my equation to solve. And I'll just choose 2 for initial guess. Now let's see what happens now. Okay. So there's my initial guess. All right. And I want to show you this graphically. So I'm going to choose do a plot of a function around the initial guess. So for x between 1 and 3. So now a plot. Actually, make sure I have no graphics windows open. So So now you plot my function, cosine x plus 2, evaluated at the vector values in xs. So here's how the function behaves. And notice the x values are between 1 and 3. The y values are also between 1 and 3. So that's a condition for existence of a fixed point, that the function g maps a given interval into itself. And to show you where the solution lies, I'll also plot the function y equals x using a red dashed line. So where these, so this is g of x, this is x, so where they meet, that's where the solution is. And it looks like it's between 1.8 and, actually between pretty close to 1.8 is where the solution lies. Okay, so we want to try to use fixed point iteration to find that. So for convenience, I can define a function handle, g, the function of x, will be cosine of x plus 2. Now I don't have to type out a formula every time I want to perform an iteration. I can just do x equals g of x. So my initial guess is 2. All right, so I'm going to plot x, g of x, and a red circle. All right, so that's where my initial guess is. Let me make this. Want the x and y, want the aspect ratio to be 1. Okay, so now I will get an iterate. 1.58, so pretty far away. So went all the way over here. And then I'll carry out a couple more iterations. But back over here, you can see there's a second circle here. And then it bounced back over here. And that's what how this will continue. I keep going on opposite sides of a fixed point, like ping pong. Okay. Now, here's an alternative iteration. So instead of simply x equals g of x, I can do x equals x plus g of x over 2. And the reasoning here is, since we're bouncing back and forth like this, it seems like if I were to take the average of these iterations, successive iterations, then that would put me much closer to a fixed point. And that's what this is doing. X is an iterate, g of x is the next iterate, and now I'm taking their average. And if x equals g of x, then this equation is satisfied also. So now if I do that, okay, so I'll set my initial guess back to 2. Then I'll have x plus g of x all over 2. That puts me 1.79. So now I'll plot that value using a black circle. So my initial guess is at 2. And look, very close to the exact solution in one step. And then I'll do it again. It didn't change very much. And I'll plot it as a black circle again. So it really is on target. So why did that iteration perform so much better than the other ones? These are things that we need to know about the convergence behavior of fixed point iteration. Any questions about these examples up to this point? So, first, as I mentioned earlier, the condition for existence of a fixed point, Brouwer's fixed point theorem, tests applying this. If G is continuous and it maps the interval to itself, you can use the intermediate value theorem to prove that x equals g of x has to have a solution somewhere in the interval AB. If, on top of that, g satisfies what's called a Lipschitz condition, the difference between g values is bounded by a constant times the difference in x values on the interval AB, where the Lipschitz constant L is less than 1. Then we say that g is a contraction, and under those circumstances, a fixed point is unique. Fixed point iteration is guaranteed to converge for any initial guess in AB. That's called a contraction mapping theorem. Now, if g is also differentiable, then you figure this, if we were to divide both sides by x minus y and let x approach y, then we'd have the derivative. We also use the mean value theorem here. So if g prime in absolute value is bounded above by some, so you can think this also being a Lipschitz constant L, and L is less than 1. So in other words, absolute value of g prime is bounded away from 1. So it's not exactly the same as saying that g prime is less than 1. Then again, g is a contraction, and fixed point iteration will again converge. So that's how we know whether fixed point iteration is going to work. So we write our equation fx equals 0 as x equals g of x for some g. We can use this to get an idea as to whether g is going to work. So with this information, we can return to the examples. So for the first one, okay. So my g is cosine, so g prime is minus sine. So and sine is going to be between minus 1 and 1. It's strictly less than 1 on the interval 0 to 1. So we do know it's a contraction. But if we investigate that, the fixed point that I got before was this value. So I'll go ahead and substitute that into the derivative. So the derivative is minus sine of the fixed point. Right, so we want this value to be as small as possible. So the smaller g prime is at the fixed point, the faster convergence will be, but this is not small. So that's why, so in fact, you can solve this equation more rapidly using bisection than with this choice of fixed point iteration. So g prime is not much less than 1 in absolute value. That's why the convergence is slow in that case. Or the second example, x is x squared plus 3/16. All right, so derivative is 2x, so we evaluate the derivative at the two fixed points that we have, 1/4 and 3/4. In the case of 1/4, the derivative is less than 1. At the other fixed point, it's greater than 1. So it's called an unstable fixed point. The fixed point iteration will fail in that case. That's why if we chose an initial guess between 1/4 and 3/4, no matter how close to 3/4 it was, the iterates would be pulled back towards 1/4. So the unstable fixed point will repel iterates when they're close to it. For a third example, x is minus natural log of x. So here's our derivative, but x is between 0.5 and 0.6, so minus 1 over that is going to be too large. So that's why that iteration diverged. But if I rewrite the equation as x equals e to the minus x, here's our derivative, and for x between 0.5 and 0.6, this is going to be less than 1. So the key rule here is that we use the fact that x equals g of x is equivalent to this equation, and you can get that by applying g inverse to both sides of this equation, and you get this one. And we're using the fact that the derivative of an inverse function is 1 over the derivative of the original, evaluated at the appropriate point. So that's why if g prime is greater than 1 in absolute value, go ahead and take the inverse. You're taking the reciprocal of that derivative, it'll be less than 1. So rearranging the equation that way to effectively use the inverse is a way to fix fixed point iteration. Okay, so in this case, so minus natural log of 0.5, but really it's, so this is derivative, yeah, so it's greater than 1 absolute value. Okay. Whereas here we have e to the minus 0.5. Less than 1 absolute value. It's not great convergence, but at least it will converge. And then finally, this example, x is cosine x plus 2, so your derivative is minus sine of x. And the fixed point, this was as close as I got to the fixed point before. We have minus sine of this value is very close to 1 in absolute value. So that's why convergence was horrible in that case. It would take it forever to converge, bouncing back and forth like that. But now, when I use this, g prime is roughly equal to minus 1. Okay. So, okay. Yeah. So what happens in this case, I have 1 plus the derivative all over 2. So I have 1 plus approximately minus 1 over 2. So h prime, so this modified iteration, has a derivative of roughly 0 at the fixed point. So that's why its convergence is so much more rapid. So it's all about making that derivative as small as possible. Questions about what happened with these examples? Now, looking at how the error behaves, so the error after k plus 1 iterations, that's the same as g of xk minus g of x star, because x star is the root. So x star equals g of x star. But now I can Taylor expand g of xk around x star. And this is what I get. And we see that the new error is equal to the old error times the derivative plus some lower order terms. So that's why this factor here, g prime of x star, that's the asymptotic error constant, or its absolute value is. But what if the derivative happens to be 0 at the fixed point? Then this term will go away, and this is the leading error term. So now you're going to have quadratic convergence, and this is your asymptotic error constant. So g double prime at the fixed point over 2, assuming that is not 0. Otherwise, it would be cubic and so forth. So in certain cases, you can get higher order convergence. But it just depends on g. Oh. I had something here, but I guess I didn't fill it in. And this is something that's discussed in text in section 10.3 that the idea behind relaxation is trying to choose lambda, parameter lambda, to be as so that g prime is as small as possible at the root. We'll try to guarantee convergence, and that could be achieved by relating lambda to the derivative. So the ideal choice would be lambda is minus 1 over f prime of x, where x would be your latest iterate. And that leads to what is known as Newton's method. So it's one way, not the only way, to derive Newton's method. Okay. I'll give you the gist of this. It's often convention to use a minus. I happened to use a plus earlier, but okay. All right, so if we assume that f prime at the root is not equal to 0, then you conclude that f prime is positive for x near x star, just by continuity of that. And if we assume that f prime is continuous, then some interval surrounding x star, f prime has a minimum and maximum. So, all right. So you show it's possible to choose lambda so that the derivative, absolute value, is bounded away from 1 by some constant L for x sufficiently close to x star. And what you do is you choose the optimal value is lambda equal to 2 over little m plus big M, where little m and big M are lower and upper bounds on f prime. If we're working on an interval where f prime is known to be non-zero. All right. And as the integration is converging, you choose small enough interval that so effectively it's converging to 1 over f prime at the root. So so if you let lambda k vary to iteration, lambda k converges to 1 over f prime at the root. So what this suggests is letting g of x to be x minus f of x over f prime of x. And if you do that, g prime at the root turns out to be 0 And from what I showed you earlier, the Taylor expansion of G, that's a quadratic convergence. And this is Newton's method. So I'll talk about, or I'll review on Monday. So this idea of using some sort of scaling factor with, it should be just plain old f, not f prime. That's what relaxation is. So lambda is called a relaxation parameter. Okay. Actually, I can also remember what the constant L turns out to be. In this case, it turns out to be there's always actually going to about loss of generality. Dang it, stop it. I'll assume a derivative for this discussion is positive. Okay. So everything being positive, that then you can see that this constant L is guaranteed to be less than 1. So that there's a bound on the derivative. Although as convergence occurs, these values will have bigger and getting closer together. So the L's will essentially go to 0, which is what you'd expect actually for more rapid than linear convergence. Okay, so that's the rundown on fixed point iteration. So next Wednesday, when we get into chapter 11, I'll talk about fixed point iteration for a system of nonlinear equations and to generalize these convergence results for that case. And the method is still essentially the same. Is just doing x equals g of x, since it said g is now a vector value function. X is vector. Okay. Now, are there questions about either this or any ongoing homework? Whatever you got.
I have a question on the Koleski problem.
Okay.
Number 12.
All right.
And my question's more about the what you want the end result to be in this problem, because my instinct was to just include an error message if the matrix was not positive definite.
Okay.
But that stops the function and never returns the is pos def.
Okay. So
do you want us to return like an imaginary matrix?
Okay. All right. So this is a problem question. Okay. Yeah. So in that case, go ahead and let the computation continue. Yeah, you would end up getting like a complex matrix in that case. But then what happens is, once you detect that there's a problem, that's when it's set is pos def to 0, or false.
Mm-hmm.
So it'll like fail gracefully, which is different behavior than what MATLAB does, where with control function it'll just bomb.
Okay. Thank you.
Yep. Other questions of any kind? This was SOR or SOR?
Yeah, that was just messing up the M and N.
Oh, okay.
That's all my problem was.
Oh, okay.
I say that's all, like that was easy to fix.
Oh, okay. Alright. Alright. Alright, I guess we're calling it good for that.